welcome to our final session of the day. This is going to be Bob Martin, the Wizard of Make, amazing title, at Microchip, who's going to be telling us about an introduction to the AVR-IoT Cellular Mini Development Board. Take it away, Bob, whenever you're ready.
Perfect. All right. So I am Bob Martin, the Wizard of Make for Microchip, and hopefully you're seeing me in the bottom left-hand corner and what's called the Enviro Cube up on the main screen. But I'm going to talk about what this thing is based off of, and I'm going to talk about the IoT Cellular Mini, which we released earlier this year, which is one of the lone 8-bit IoT boards out there.
Okay, let's just walk through some slides on the Cell Mini board, and then we'll get to some real applications. So the Cell Mini board, much like other IoT boards, is targeted for low power applications. It's paired with a Sequans Monarch 2, and by paired with I mean the AVR128DB48, which is a relatively new-ish AVR microcontroller, and it's got some special stuff that makes it very well suited for edge nodes, and along with makes it easy to pair with a Sequans modem. So this Sequans modem, again, is a Monarch 2. It supports NB-IoT and LTE-M. Currently only LTE-M right now. We're awaiting a modem firmware update, which can be done on board to supply NB-IoT capabilities. We also have the ECC608A Secure Element, so that provides pure certificate exchange connections with cloud servers like AWS and Azure. And along with it, to make it much more friendly in the makerspace, which is a unique thing for this board, it not only has a onboard Qwiic or Adafruit Stem ST connector, which now gets you access to a wide array of I2C based sensors from both companies. It also has a Adafruit Feather featherwing footprint. So Adafruit featherwings will just pop directly onto this, and that's been used in implementing some demos that we've done with GPS engines from Adafruit. Another bonus is that it comes bundled with a SIM card from TruePhone. We are partners with TruePhone. You get a 90-day free trial with a 150 megabyte cap on the data, which should address literally almost every IoT app that you're going to be using for this type of RF channel environment, i.e. an LTE-M type of arrangement. We also supply an antenna, so it is a full plug-and-play experience. Interestingly enough, this board is only supported in Arduino right now. There are some bare metal and MCC Harmony apps coming online, but it was primarily intended for the makerspace initially to get both this LTE-M and this AVR DB part out there. One of the specifically cool features of the AVR DB48, and it's got quite some enhanced features over those of you who are familiar with the Mega 328P, which is the baseline of the Arduino Uno, is it can supply 2 voltage rails at the same time. There are 2 VDD I/O pins coming in. There's the main VDD I/O pin, and in this diagram, that's represented in the reddish or the light red, pinkish area. And the green part is the secondary voltage domain. Now, the reddish area and this specifically implementation is at 3.3 volts. And in order to talk to the Sequans modem, although it's supplied with 3.3 volts, its I/O ring itself through the UART sits at 1.8. And we now also run the ECC608 on that secure element at the same domain. and that allows us to avoid use of any voltage translators, and this comes in useful since these two voltage domains, you can run the voltage domain between 5 volts and 1.8 volts without worry about power supply ramp up sequences or anything like that. There is, you can see there's a temp sensor and a RGB color sensor on another I2C bus. So now you also have two I2C buses. There's also an onboard debugger, but let's go into a little bit more of the AVR DB. The multi-IO level shifters, I introduced that in the previous slide. We have multiple low power modes. The DB microcontroller family is fairly analog heavy. There's two internal op amps, and these are op amps modeled after a fairly popular op amp family for Microchip. The ADC has been bumped up to 12 bits of resolution. Another interesting thing which makes it very suitable for low power is we have an internal 32 kilohertz oscillator. However, if you need really precise timing support, you can add a 32K crystal outside and run. Both of these run in a completely asynchronous time domain, and you can switch the main clock back and forth between them. You might have noticed from the previous slide, and I mentioned there are multiple I2C SPI and UARTs, again spread across that multi-voltage domain. And one big improvement that's in all of the new, what we call the DX or the EX or the AVR series coming out now, is the core support now. The actual core, or the AVR core itself, now has full 24 megahertz support down to 1.8 volts. The what I call the classic line of AVRs tended to have to descale speed as you drop the supply voltage. No longer. You're full 24 at 1.8. As I mentioned, the whole Arduino core environment is supported by an MCU core instantiation called DX Core, which is created by Spence Condi. And we're also adding support to import these sketches into MPLAB-X. So you can add full source level debugging capability to your Arduino sketches. And that's, I've been teaching classes on that for several years now through Microchip Studio, and we're very, very close to releasing the full sketch import utility for the DX cores. Now, all of this is supported on this board by the onboard debugger. So not only is this going to give you the ability to do source level debugging, it is a professional ID in MPLAB-X, but another key concept is you don't need a bootloader anymore, so we don't have to sacrifice any of that flash space for a bootloader, because the programming interface on the new DBs or the new DX cores is a simplified 9-bit UART. I'm not going to go into a lot of detail on this. However, obviously for over-the-air updates, we will be needing a secure over-the-air bootloader, and we're working on that, along with Azure and AWS, and to support those using that secure element, obviously, because updating securely is very important. Here's the GitHub link for Spence's DX core. That supports the core. The entire modem is supported by the AVR-IoT Cellular Arduino library. Now, we did a pull request, and Arduino added this to the global library search pattern. So for those of you familiar with Arduino IDE, you can just search for this library without having to add an extra library or chip support URL to the environment. And as you would expect, it handles all of the modem connectivity cases, you know, HTTP, S, and MQTT mode. Deals with the power save mode for the modem. And as I mentioned before, the secure element, we have the certificate exchange. TLS is supported, and we throw in quite a few examples in that library. Some landing pages that are excellent documentation resources for this board. The base is iot.microchip.com. There is, here's a direct pointer to the GitHub where the base level library sits. The part number for the board is there, not intuitive, and the resale price is basically 60 bucks. And it's available through Avnet right now. We have plenty in stock. Moving forward, this is what I call the Enviro Cube demo platform. This I put together over a couple of weekends. The structure itself is MakerBeam 10mm. I'm not receiving any promotional consideration from MakerBeam. I just happen to like it because it saves me a lot of time in prototyping hardware without having to sit there and wait for 4-hour 3D prints. So I mashed together the AVR-IoT cell board and 3 sensors, an SGP40 air quality CO2. Now this is true CO2, an SPG30, which is a volatile organic compound and emulated CO2, and a BME280, which is a fairly well-known sensor. So the first 2 are from Sensoron, and a good company. I like their sensors, especially for environmental monitoring. And Bosch, of course, making the BME280. And you will note in the pictures that they're all daisy chained with the Qwiic connectors. So that allows me to swap in and out sensors quite quickly. And that was one of the reasons why we added the Qwiic connector to that board, to implement exactly what you're looking at now. One thing I wanted to address that sometimes people lose sight of, and we're digging a little bit more down into the technical stuff, but I just would like to remember all of you who are daisy chaining a bunch of I2C sensors, if you're getting funky responses, and if you have a scope handy, please have a quick look at the rise times, because that's going to really limit your ability to obviously read data. And here we've got rise times that, you know, the leading edge, right? And that's the RC time constant of that massive I2C bus, or not massive, but daisy chained I2C bus looks pretty healthy. Every Qwiic or Stemma board generally has pull-up resistors on it, and going into low power modes and just slamming the I/O pins on the microcontroller high by, say, disabling the I2C bus is a good way to minimize leakage. But that also takes into account that if you're active, you're transmitting, you're burning power in the I2C pull-up resistors anyway, but it's pretty much background noise compared to an RF modem. Anyway, I guess the long story short, just be mindful of as you're increasing the length of the I2C sensor interface cables and how many I2C sensors or actuators or whatever, you just have a peek at what's going on in the I2C bus in the time domain. That may solve some headaches that you've been having. Anyway, let's move on to actually talking about the Enviro Cube demo and hooking it up to the HiveMQ platform.
As promised, here is a quick overview of the hardware. Let's get back to the business end of the equation. So the star of the show is right there. That's our IoT mini cell board with the antenna popping off the top there. I just put it on a little piece of plastic because I'm going to be adding some more sensors on the top, some optical sensors and such. again, that antenna supplied, so that's all good. Access to the USB connection through that direction, but we are looking at now the sensor deck. Oh, by the way, this is MakerBeam 10 mil. I'm a big fan of MakerBeam when it comes to things like that. It gives a quick way to set up chassis, and so I don't have to sit there and wait for hours for a 3D print on something. I'm not getting any professional consideration from MakerBeam. I just like it, so some of you may be familiar with it. And then on the sensor deck side, all connected via Qwiic extension cables from our friends at Adafruit. Starting from left to right, we have the SCP-40, the true CO2 sensor, the BME280 on the bottom from Bosch, and then the SGP-30 from Sensoron, again the CO2 and the TVOC eCO2 sensor, both from Sensoron, sitting there, and again all nicely daisy chained through a Qwiic connector. So this is the Enviro Cube demo platform that is going to be generating the data we're going to be seeing in a minute. So and I'm going to be adding some additional sensors to this. Like I said, optical sensors, light and UV index, just to get the whole sensor package complete. All right, so on we go to having a look at the software. First, we're going to start with the Arduino sketch that we're using. You'll notice that this is IDE 2.01. If you're not using 2.01, I'm going to personally recommend that you give it a shot. It's a far better editor, and you can see the glorious better color highlighting. There's some other features that I'll let you discover on your own. I just want to go over, however, exactly how easy it is to run a, and this is an MQTT demo, and I'm using HiveMQ, and I have no, I'm not receiving any promotional consideration from HiveMQ. As I was wandering around looking for an MQTT solution, one of the things that was very compelling to me was that they have a WebSocket dashboard that makes it trivially easy to confirm your data stream without having to go through a lot of dashboards. And as a bare metal old school developer, I really appreciated that, and I'm going to show you that feature very soon. I'm not going to go into like gory detail of everything in this sketch. We're going to get this example and some documentation loaded up on that iot.microchip.com website so you can reproduce it. Obviously, some of the information here is specific to me, and of course will be changed after this gets published. But let's just go over some real quick basics on what we need to be doing here. So some of the basic libraries that you'll see in the examples is ECC608. Even though we're not using that, there are some hooks that just need to be resolved in the LTE library, which comes there. I have the LTE library and the DX Core library already installed. I'm not going to go over those installation instructions on this video. It's clearly given in the documentation on the website. I also included MQTT client.h. Again, that's part of the LTE library, and as well the Arduino libraries as well, and Sequans modem and low power. All these are part and parcel of the LTE-M library that gets installed. I want to just point out that this is a fairly legitimately understandable block of defines for how we're connecting to HiveMQ's broker, or one of my MQT brokers on HiveMQ.
I've got a subscription topic and a published topic. We're going to be seeing that as a subscribe topic on the WebSocket. The port numbers, well, let me back up. Their example URLs are really long. You can, for a paid subscription on HiveMQ, get this random number generator URL front end shorter, only up to a point, but it works. The free broker signups give you more than enough for testing. The ports are perhaps different, or for those of you who understand or recognize TLS ports, HiveMQ only accepts TLS connections, which is I think good. The configuration, and then again, is we're looking at a true TLS is true. This is a keep alive for a ping through the modem stuff or back through their broker, which is 60 seconds. We are not using the ECC, and that means we're not doing a formal certificate exchange using the ECC like we do with AWS. I want to approach HiveMQ so we can discuss doing a root trust certificate exchange, so we can add that extra level of security that you get with an AWS connection. But I wanted to demonstrate just a normal TLS connection without the overhead of a certificate exchange. I've added, because it's TLS, we have some username and some password access that we need to authenticate with to log into the broker, and those are shown with Enviro Cube 1 and Bugs Bunny. I also take advantage, of course, now, because all this board is Arduino supported and Qwiic supported. I just took a selection of sensors as I went over on the tour of the hardware platform, and here's just all of the Adafruit and Sensoron direct header files and the libraries, which are again easily installable through the Arduino library system. Some basic structures I just put together for measuring data. You can observe at that leisure. Setup is essentially just setting up the TLS, which I'm going to go into a bit, and then connecting the LTE and connecting the MQTT broker using that collection of data here. The LED control, this is a library that we included in the LTE package that has direct control over the 4 LEDs on the board. I set it to manual because the LTE library can grab a hold of these automatically and relay status during connection. That's a personal choice. I just shut it. I grabbed manual control and shut everybody off. There is another facility called log raw or log. You'll see log debug, log info. That's just getting a hold of the serial port. For those of you curious, if you don't have to use the log facility, it is serial 3 is the debug CDC UART coming through the nano debugger CDC UART thing. Log just uses serial 3. TLS config is a call to a direct object and as a Sequans controller that gets created my apologies, it's created basically right there. It's already created in the library. Sorry for that brain fart. However, what we're doing is the Sequans controller, the write bytes again, the Sequans controller is essentially an AT command set, as everybody's familiar with. All we're doing is writing a direct AT command sequence. I'm not going to go into the details, but all this is saying is use the security slot 2 in the system on the ECC and accept any TLS encryption algorithm that the website wants to negotiate with. And once you're set with that, then your TLS configuration is all set. Connect LTE is pretty straightforward. Just, if LTE begin, this is a thread blocking call, and there are ways not to make it thread blocking. It will, because eventually bleep out. Right now, this will never return, depending on some factors. And this is just an ugly escape sequence on my part, which I'm going to improve. The Connect MQTT is a little bit more intelligent. It's again a call to the MQTT client with all those parameters that we had discussed up in the previous block. We have the ability to sit and spin until we connect, and then elect to drop out. I set a connect attempt of less than 10. That generally, that's adjustable, obviously, right there. I found 10 is a good go, no-go thing. And then just following through that we're connected, or else, pop an error out. Now, this comes back, this is a good discussion that I need to bring up. When you're configuring your SIM card for the first time, the reason I'm not dropping out or using the same type of structure here is sometimes, because TruePhone is based in Europe, sometimes it takes a little longer than you would think for everything to ripple through all the carriers. TruePhone has partnerships with all major carriers in North America and in Europe. And I can speak to North America specifically. It defaults to AT&T, then it's Verizon, and then T-Mobile. Okay, but if you're near an AT&T tower, that's who you're going to be talking to first. It is transparent, but the handoff is not automatic. If you lose connection, you will have to, the connection needs to be reset, and then you reconnect. And there are ways to pull the specific carrier out of the modem using some AT command, just like this this TLS configuration. The rest of the main loop is pretty simple. After I knit all the sensors, I just sit in the loop and I look at the 280 and the SGP30 and the SCD40. I format the scan message, and then I publish the scan message, and I wait 5 seconds, because that's pretty much how fast the SCD40 can sample CO2. And in an environment setting, even 5 seconds is pretty quick. That's a pretty high duty cycle, depending on where you are, but in a remote industrial setting, 5 seconds is actually pretty quick for temperature, pressure, and CO2 updates. I have some system sleep. There's some low power stuff in there that I've de-scoped right now, and some shutdown stuff. I'm working on improving some of the low power numbers right now. The updates will go up to the website once I get all that worked out. And nothing groundbreaking. It's just a string where yes, sprintf is very useful. I find it a lot less tedious than doing a bunch of serial prints. And especially in this case, you have built-in floating point support up to 2 decimal places in the Arduino standard output library. Anyway, publishing is very, very straightforward down here. And all this is just, the rest of it's just initializing the sensors.
The one thing to be careful of, and which I wanted to bring out, is, as I mentioned, the DB has multiple I2C interfaces. It's wire 1 where the Qwiic connector is sitting on. Okay, so as you're developing your applications, make sure that you call out or begin wire 1 either with begins the SCD40 wants a specific call, whereas as you can see some of the other sensors you just pass a pointer to the wire 1 object, and that gets taken care of in the build, and I'm going to go over to the build and the upload. So let's do that. So remember I was talking about we don't need a bootloader anymore. Well, we do with the over-the-air update. But what we want to do is take advantage of the UPDI programmer, because the nice thing about using the UPDI programmer is it lets you keep the serial port open at the same time. Normally, those of you who are very familiar with the Arduino environment know that a lot of you forget to close the serial port if you've got some serial traffic going on. And that's always annoying. You know, you get into the cycle, but I'm going to prove this by I'm going to move in a teraterm instantiation, and I'm going to connect it to the serial port, which is 115.2, and we're going to see some traffic here in a minute. In 5 seconds. Now this is a session that's been running, but I'm also going to pull up this, and I'm going to upload using programmer. And down here, all the magic happens. I do have verbose compile and upload, and I'm going to show you that I am still connected through the serial port. And down here at the bottom we have the UPDI activity, right? Because it's a separate channel on the embedded debugger. So I find this very useful, and I hope you will too, in the ability to run sketches or download sketches. So these are all the steps. LTE Connect, it's going to go out and talk to the operator. So I know I'm here in Silicon Valley. I connected to AT&T. Here's the broker connect, and the broker's connected. And there's a bit of a delay here again because of that 5 seconds. Not a fault of the SCD40. It's just the way it works. And I'm going to also now, let's go over and have a look at the data stream I'm pushing out. I'm numerating the scans. Because I have multiple sensors, I have multiple temperatures, and I want to point out that the BME 280 is one of my favorite pressure sensors, and but there's also a temperature sensor on the SCD40, and right now that's an interesting big differential of almost 3 degrees centigrade. But you have to understand, integrated sensors tend to self-heat, so that's one thing you need to be careful of. The pressure here, we are currently in a rainy situation right now here in the Bay, thankfully. So you can see the pressure is below 1,000 millibars, which I haven't seen in a long time. It was actually a little over 1,000 this morning when I was running through this. The SGP30, okay, the humidities are kind of lining up, but you can see some differences there. So one of my big things is, what is the truth environmental monitoring? So the winner of the temperatures is going to be the addition of an LM35DH, which runs for about $22 a piece. It's an analog sensor, back from my days in National Semiconductor, which is going to give me hopefully the analog truth. But again, a man with 2 watches is never sure what time it is. The SBG30 also gives you something called equivalent CO2. And for those of you who are familiar with it, you know it baselines down at 400 parts per million. However, the last column is the true SPG40, which is now sitting at 955 because I've been talking for a while. The TVOC is bouncing up and down, and I'm going to take an arrow duster and just shoot near the sensor array. That's what the hissing is, and you're going to see things go off the charts for TVOC, and you'll see that the ECO2 is maxing out or is hitting large count numbers, whereas the real CO2 went down a little bit because there's no CO2 in a superduster can. So the ECO2, as clearly mentioned in the sensor on datasheet, is a synthetic number. So I would highly recommend, and I'm not trying to throw shade on Sensoron, I love their sensors for environmental. If you're looking for volatile organic compounds, SPG30 is a great way to go, but their new SPG40X line of the 40 is a better way to go for CO2 because it's using an actual measurement technique. And I'm seeing a lot of better and more cost-effective sensors measuring CO2 because it is a lot of IR absorption line stuff rather than synthetic stuff or hot plate stuff like VOC sensors. Okay, the one last part of the equation is the HiveMQ WebSocket interface, and I'm just going to drag this in. So we're at about like scan 38. So I'm just going to drag this into the frame, and as you can see, it's basically all I need for debugging, because I'm getting confirmation that that's the equivalent of the string that I'm punching out to the virtual terminal or the teraterm terminal, and that makes me happy. I didn't have to write a client. I didn't have to bring up another board to pull that subscription down. I'm subscribed to the sensor scan topic, and the data showed up immediately. And as a bare metal guy, or as not a web developer kind of guy, I really appreciated that simplicity in validating the data, because then I can go to the software teams, or as a developer, you can rest assured that, hey, look, I've got that MQTT topic published, and I can prove it. So I appreciated that simplicity because it was a zero code option for me. So there we have it. This is a overview of basically how simple it is to get an MQTT client going with the AVR-IoT Cellular board. And as I said, I'm going to get some of the low power stuff more integrated onto the environmental cube, and then go on from there. So, all right. So thanks a lot for listening, and look for the update on iot.microchip.com. Again, this is Bob Martin, the Wizard of Make for Microchip, and I appreciate you listening in.